Hello everyone, I hope this video finds you well. Today we'll be jumping into logs, which we just spent the day yesterday with exponentials, get a little bit of a background, and then we will spend more time with logs because we can do more with them, and also logs and exponentials are super closely related. So we needed to understand a little bit about exponentials before we get into logarithms. If you have some preconceived notions about logs, like if you remember them from Algebra 2 and you remember them being challenging, it was the first time that you had ever seen them. So I will encourage you with this, that I have a lot of students in PreCalc that will tell me, oh, I don't know why I found this difficult in Algebra 2. And probably because it was the first time that you had ever seen a log. It was crazy. So first, I'm going to give us a little bit of background. Why do we have logs? And then we'll get into some of the things that we can do with them. There are a lot of details in how they work because logs are their own operation that we'll ease into it. We will spend several days just laying some groundwork for what logs can do. So first, yesterday we had solved equations like 10 to the x equals 7. And if you remember from yesterday, hopefully we do, it's been 24 hours, that you would get the same base raised to a power in order to solve it, because we found that if the bases were the same, the exponents had to be equal to each other. So in this case, maybe I would be trying to get 7 to be the same base to a power as 10, or rewrite 10 as 7 to a power, and hopefully we're already having a little bit of like, because there's nothing that I can raise either of them to that is the same base to a power. In fact, neither of them are perfect squares or perfect cubes, so it doesn't work that way. Or if we had something with decimals, what do we do with something like this? If I'm trying to get the same base to a power and I have a number like 1.429, what do I do with that to get the same base to a power? And the answer to that is that we had to have logs. Logs are super useful in solving something like that. We'll do that eventually. They also have the power to take very large numbers and put them into a scale that is easy for our brains to comprehend. In the same way that if we're looking at millions and trillions of something, it is really hard to imagine what it's talking about. Like if I told you we're going to take a test in 1,000,000 seconds, you would be like, okay, I have no frame of reference for what that is. It's a really large number. Versus if I tell you we're going to take a test in 12 days, you've chunked all of those seconds into a scale that is easier for you to handle. So by taking a really large number into something smaller, it's a lot easier to imagine. 1,000,000,000,000 seconds, now I'm like, I don't even know how that relates to 1,000,000 and 1,000,000,000,000 seconds. It sounds like they'd be kind of close to each other, where 1,000,000 seconds is actually 12 days and 1,000,000,000 seconds is 30,000 years. So that's a big difference, but whenever we put it down into days and years, we have a better grasp of what that actually is. That's what logs do for us. They take something very large and put it down to a scale that we can deal with because it has to do with exponentials. We're raising something to a power when we're talking about logs. So we can go from something where if we're raising, these are all base 10, if we're raising 10 to the 0 power, that would be like a single item, it's one thing. Where if I could go to just the power of 23, so 10 to the 23rd is the number of molecules in a dozen grams of carbon. That doesn't mean a ton to me, but I think it has to do with Avogadro's number. And then if you get to the power of 80, 10 to the 80th power, that's the number of molecules in the universe. How do we know this? I don't know. I guess I probably Googled this at some point. Maybe it's different now. Are there more molecules? Let's not get into that. Anywho, we can go from raising our power from 0 to 80 to go from one single item to the number of molecules in the universe, and that's the power of exponentials and logs, that I can understand what 0 to 80 is. I wouldn't really understand the number that is a 10 with 80 zeros attached to it. That would be gigantic. What we use this for in the real world, things that we were taking large numbers and putting it down to a scale that makes sense. When we're looking at earthquakes, the Richter scale is based on logarithms. they take the magnitude of an earthquake and put it down into a scale where we can just say it was a level. I should have looked at this beforehand. What do earthquakes go up to? Does 4 make sense? I don't know. A level 4. Why not? Fact check me. We use them in astronomy because we're looking at very large amounts of space, that you're looking at really large lengths, and so putting them into logs, we can talk about things, that level raising to the 80th power instead of 10 with 80 zeros afterward. With decibels, very similar to the Richter scale, where they would convert noise levels into decibels using logs so that we put it on a scale that makes sense to us. Okay, so let's look at how logs actually work. And a lot of this is going to be trying to jog our memories in how logs work. Looking through this, I think we will remember some things here. Okay, so when we're looking at a log, the way that a log works, and these all have what they're equal to, so we're not like trying to solve anything, I'm just showing you this is what a log is saying. Whenever I see this log base 2 of 8 equals 3, that means we're saying 2 to the 3rd power equals 8. So it kind of goes in this, like an alligator mouth, that 2 to the 3rd power equals 8, 5 to the 2nd power equals 25, 3 to the 3rd equals 27, 2 to the 4th equals 16. Where if we are missing what it's equal to, so if we just have the log base 5 of 125, sorry, I'm trying to make this straight. Log base 5 of 125, it is asking us the question, 5 to what power is 125? So the answer to a logarithm is an exponent. That's one of the reasons why they are so closely related. And if I'm saying 5 to what power is 125, I would be raising it to the 3rd power. Okay. Same thing here. See if you can answer the 2 to what power is 32. And for something like this, I always start at 8. It's like the only one I have memorized. 2 to the 3rd is 8. And so I know to the 4th is 16, and to the 5th is 32. But we could be missing other parts of it. If I've got log base 7 of what is 2, that would be saying 7 to the 2nd power would have to equal 49. We could be missing the base and be saying what to the 2nd power would equal 81. So 9 to the 2nd power would equal 81, which we'll look at here in a minute. We can definitely put this into an equation where I'm saying like 2 to what power is equal to 32. And we can even solve it like we did yesterday by changing the bases. It's a lot more important that we're able to do that when it's a little bit more challenging than this. We're just trying to get the handle on what logs are about right now. So to give us some vocab here, because I've already said some things about bases and powers. A logarithm itself is a power or an exponent, and by that we're saying that whenever we're looking at log base n equaling x, we're saying that b to the x equals n, so that x is an exponent. So if I were to write this from logarithmic form to exponential, I've got b to the x equals n, so that x part is the exponent. And that's why we say a log is an exponent, because it's equal to the exponent. And that's important because it will actually behave like an exponent, and we'll get to those properties tomorrow. The base for both of these, in the log it's called the base. For the exponential over here, it's still called the base. So the base of the log or the base of the exponent. And then the last part of this is less used, but the n here is called an argument. Argument. And every time I write that, I debate with myself whether that e is there or not. Couldn't tell you. Okay, so if we are rewriting from logarithmic to exponential form, then the answer to this log is 2, and that is the exponent. We're saying 6 to the 2nd power equals 36. It's a lot easier to deal with when you have all numbers though. If you're trying to rewrite into exponential form and you don't have all numbers where you can confirm that that is true, then we have to know how logs work. So giving yourself an example of just rewriting from log to exponential form, that this is saying w to the third power equals 8. So making that alligator mouth. So what we haven't done is going the other direction. If I'm starting with an exponential, so we'll start with all numbers first, we can see how it works. It actually works the same way as the alligator mouth. So I would say log base 4 of 64 equals 3. So log base 4 of 64 equals 3. It's also important to see that it makes sense. My base becomes the base of the log. It is equal to an exponent, so I know that's what my log has to be equal to, and then 64 is the argument. It's what my 4 to the third was equal to. Okay, so go ahead and try rewriting your 81 to the x equals 5 in logarithmic form. And pause the video anytime if you're wanting to try something on your own first. We would have our log base 81, it's a big base, but that's fine, of 5 equals x. Double checking, okay, my base here, it's a base here, I'm equal to an exponent, it's equal to an exponent. So we could use this information to evaluate, very similar to what we did yesterday, that if I have log base 25 of 125, first, if I'm giving something like this to evaluate, it's asking me what that exponent is, that 25 to what power is 125. Sometimes, like when we are filling in the blanks, I can answer that in my head. I just automatically know 5 to the second is 25. But for something like this, I don't always know what power to raise it to, so that's where I'm going to rewrite it in exponential form, that I have 25 to the x power equals 125. And now it's turned into a problem like what we looked at yesterday, that I need to get the same base raised to a power, and then I can solve for x by setting the exponents equal to each other. So I could rewrite our 25 as 5 squared, our 125 as 5 to the third, and then because the bases are the same, my exponents have to be equal to each other, and x ends up being 3/2. So this is anytime I'm trying to evaluate a log. Same thing here. I'd set it equal to some variable. It doesn't have to be x. You can make it your variable whatever you want it to be. That we've got 1/3 raised to what power equals 27. Now from yesterday, what do we do first if we have a fraction as our base? We should be moving that 3 to the numerator. It does get a negative exponent. And now we can work it like normal. We're looking for the same base to a power. So I'll use 3, can't be any smaller than that. I want to rewrite 27 as 3 to the third. And then because our bases are the same, the exponents are equal to each other. So we get a -3. Oh, really, I guess the y doesn't make sense. We just say -3 because that wasn't in the problem to begin with. But that is the power that it would be raised to, which makes sense because 1/3 to the -3, if you take the reciprocal, it would be 3 to the third, which is 27. Okay, so I've got one more here. Go ahead and try this last one on your own. Pause the video. Try it out. So we're evaluating, we are rewriting where we know this is set equal to some exponent, 81 to what power equals 9, rewriting our base as, this 81 is 9 squared, and then because our bases are the same, the exponents are equal to each other, you've got a 2x equals 1 or x equals 1/2, which makes sense because 81 to the 1/2 would be the square root of 81, which is 9. so getting back to the problem that we started with, one of them that we started with, sorry, there was a word problem that went with this and we just jumped right to the end, where we had bases that you could not make the same. So if you had that 7 to a power equaling 10, I think it was, or maybe it's 10 to a power, I don't know. Or if you have decimals that are raised to a power, and so you're like, I can't get the bases the same, so what do? Well, anytime we're stuck, these exponents and logs work together. So if I am stuck as an exponential, I actually want to go the opposite direction and rewrite it as a log. So if I'm stuck here, I would say, okay, the log of base 1.04 of 1.49 or 29 is equal to that exponent. And notice that whenever I rewrite from exponential to logarithmic form, that it gets the exponent by itself because logs are always equal to an exponent. So whenever I put it in logarithmic form, that x is going to be already solved for. And then I'll just go to my handy dandy calculator. You've got a couple of different buttons for logarithms. Get a little stuck there. So you've got these two buttons right here, the natural log and the common log that we'll look at here in a minute. But whenever you hit control and just the common log, it actually lets you change the base. That is not true of all calculators, so you've got one fancy calculator on your hands. So again, I hit control and then that 10 to the x gives you the log above, and we can put in our base of 1.04, our 1.429, and it will let us know that that exponent has to be 9.102. So x is about 9.102. This is something that we have to have a calculator for. It's the same reason that we didn't know what base to raise that to. It's because, you know, our brains weren't able to come up with the power that we would raise 1.04. Oh, it's 9.102. We have to rely on our calculator for that. So if we end up with something that we can't get the bases the same, it is going to be something that requires a calculator. Okay, the last thing that we're going to look at are two different types of logs that we see where the base is not any old number but a specific number. So the first type of special, I'll go ahead and put that at the end, ignore that. The first type of special log is common log, and it is very common, where the base is 10. Base of 10. So like those powers that we looked at the very beginning, started with one object, went to the number of molecules in the universe. This is a common log because it is useful. It is common. Our scales, you know, when you're changing from Richter, you're using Richter scale, something like that, it is common for things like that to use base of 10. So that's why it's a common log. Oh, by the way, pH scale uses logs as well. Just thought of that. So what we need to know here is that whenever I see a log and it does not have a base, it's because it is using common log. So if I see something like this, the log of 100, and I'm looking for an answer, I'm like, what? This is not giving me enough information. It's because the log is 10. Just like whenever you're taking the square root of something, I didn't have to write 2 there for you to know that it was a square root. It's the most common root. So you knew it's a square root without putting a 2 right there. It's the same concept. Whenever I don't put a 10 there, or don't have a base there, it's automatically a 10. So this question would be asking us 10 to what power is 100, and so the answer would be 2, but we would have to know common log in order to know what the base was there. So no base, the base is 10. The other one is natural log, and also named very appropriately, it is a log that happens a lot in nature. We see patterns in plants, animals, all sorts of things in nature that involve E, involve natural logs. For today, we really just need to know if we're talking natural log, it has a base of E. And also it is uses this ln as natural log. It's Latin, so it's kind of backwards. We think it should be like NL, but it's ln. Try to keep from saying ln of e to the negative 2. First of all, it's a lot of letters, But also this means natural log. So go ahead and say the natural log of e to the negative second. So similar to your common log, one important part is just knowing when I'm looking at that it is a log base of e. So we're actually not going to write in an e for that base, but this natural log means log base e of e to the negative second. So if we're wanting to look at that base, I would actually have to go from natural log to log base e. These are the same thing. And then we could know it is asking us e to what power is e to the negative second, which seems kind of redundant. If you were to set it equal to a variable, then it would really say e to the x equals e to the negative second. And of course, my bases are the same. My exponents have to be equal to each other. We're just saying -2. E to the negative second equals e to the negative second. A little redundant. We could have something like this where we're rewriting our e to the x equals 5, and just knowing that whenever I rewrite it as a log, if I end up with log base e, that this actually means natural log. So log base e of 5 equaling x is the same as the natural log of 5 equals x. And this one was asking you to rewrite it, but if we were going a step further and actually evaluating the natural log of 5, or they asked you to solve for x, it is something that requires a calculator. Because for the natural log, we're looking at a base of e. So if I'm asking e to what power is something, in this case, e to what power is 6, that's not something that I can do in my head. Remember, e is that 2.7 blah, blah, blah. So not something I can do in my head, unless it's something like this, where you have e as a base in your argument. So I'd have to go to my calculator. The natural log button is right next to the log button, where you are hitting control again, and then that e to the x right above it gives you the natural log. Whoa. And so once you have your natural log, we're just saying natural log of 6. Come on. Which equals this 1.792. Which is telling us that we would have to raise e to the 1.792 on and on to equal 6. So you can even test that out. You're like 2.7, which it's longer. You actually have an e button right there that you could raise it to that power, 1.792. And it's about 6. If you use the actual e button, I'll go back, e to the x, and then we raise it to the 1.792, you're going to get really close to 6. 6.001. We had to round up here, so it's not going to be perfect. All right, so that is it for today in logs. Thanks for hanging in. One last thing, I am going to have you all, just so we have a little bit of back and forth. It feels weird to not talk to you all face to face. I want you to go on today's post, so the explanation for today, and you're going to comment at the bottom the name of your first pet. So no explanation. You're not going to be like, the name of my first pet is, like, don't explain. Just be like, Fluffy. And that's it. So that way we can all learn about your first pet, and also people that haven't watched the video yet may be a little curious what's going on. So I hope you all stay dry and warm, and have a great rest of your day.